What we're going to do here is two experiments using homogeneous materials, currently gelatin, and we're going to induce some fractures in them which show the different fractures which result from different stress conditions. And these will be conducted in these homogeneous materials of gelatin which are representative of materials in the earth. And they will be injected through these pipes which you see here, and it will be a liquid similar to which would cause a hydraulic fracturing regime of some kind, whether it's horizontal or vertically fractured. We'll be using two different sets of apparatus, and two different fracture set types will result. These two bodies are cylindrical in nature, so that we try and eliminate any effects from the edges of these containers. And so it's more similar to materials in the ground which stretch laterally into infinite regimes. Also, we have some surface effects from the bottom and the top because these bodies aren't infinite.
Okay.
The tools that we're using to demonstrate this consist of an apparatus to lead to stresses on the cylinders, some purple dye which is mixed with water and plaster of Paris to give it a viscous consistency, and an injection apparatus which provides a constant pressure and injection through this hose into the pipe of each of the models. This particular cylinder is going to be put under stresses where the horizontal forces or stresses are very differential, where the major horizontal stress is induced by these wooden boards which are connected together with screws. The minor horizontal stress is acting backwards and forwards, and in this direction the fracture will propagate. The vertical stress is an intermediate stress and will probably not affect the results of the test. As you can see, it is difficult to squash the bottom part of the cylinder as much as the top part of the cylinder simply because of the properties of this experiment. The first step is to remove the borehole plug from the simulated borehole. And then at this point we can fill up the borehole line to attempt to prevent airlocks. This model clearly shows the vertical fracture. On the surface, you can see the outline of this fracture. Where it originated at the borehole, it's slightly larger and fatter than at the edges. This is the strike of the fracture. The whole vertical fracture is an hourglass-like shape. And from the side, you can see that a small horizontal fracture was also initiated at the borehole entry point, but quickly became vertical at the edges. Overall, the vertical fracture is completely up and down and was not affected by stresses until it reached the bottom of the container, where the stresses became more hydrostatic and the stresses of the vertical overcame the horizontal. Looking around the side of the model, you can see again the large vertical fracture with the small horizontal in the middle. And you can also see the ink that collected where the fracture turned over and became horizontal and the stresses changed at the bottom of this gelatin container. Okay, this particular cylinder is going to show the effects of radial stress on environment. In this case, the horizontal stresses, both large and small, are going to be all in the same magnitude, whereas the vertical stress should be the least stress in this particular case, and we expect to have a horizontal fracture in this particular case. After removing the false borehole filler, we can again insert dye into this borehole. Okay, you can see that the entire jello has not been filled with ink, but a large horizontal fracture has been created. If you tilt it and have a look, you can see that from the surface, a large round disc shape is very obvious on the left side of the cylinder. From the side, you can see more clearly where the fracture line has encountered the cylinder. During the course of the fracture, the stress along the edges of the borehole created a pathway for the dye to go upwards and create a small vertical fracture. But it is clear that horizontal fracturing dominated this stress field.